it reaches some height, h1, and at height h1, we have what I'm going to call V1 upward. So the thing rises to a height h1 with this acceleration. The engine cuts off, and now it has an initial speed at h1 of v1, and the acceleration from this point onward is equal to minus g. It eventually reaches a height h2, and h2 is equal to 960 meters in the numbers I'm given anyway. And what? V equals 0 at this point, because this is the turning point where the rocket will turn around and fall back down. Okay. So h1 is equal to 1/2 a t squared, where t is the amount of time that it takes to get to h1. So where does this come from? Well, we have a kinematic equation that says that y equals y0 plus v0 yt plus 1/2 a t squared. Well, y is h1, y0 is 0, v0 in the y direction is 0. And what is the time? Well, the time is given to you as capital T, and that's what you're trying to find. So that's our first equation based on the kinematics. And V1 is equal to A times T, right? That comes from the kinematic equation V equals V naught plus AT. So again, V naught is 0 for this portion, this first portion of the motion. So in regime 1, V naught is 0. So, and T at this point is capital T. So we get that. So let's use okay. So let's use our kinematic equation, V minus V0 squared equals 2A y minus y0. And let's apply this equation at this point, between that point and that point. So at H2, V is 0. And the initial speed right here at this point is V1. Now, A in this region here, in this regime, is minus G. So that becomes minus 2G. And we have H2 minus H1. All right, that doesn't look very helpful, but it is, because we know all of these quantities in terms of the unknown capital T. So minus V1 squared is minus A squared T squared equals minus 2G. H2 is known, 960 meters, and A is known. Minus, now what's H1? 1/2 a t squared. All right, now you can solve that for capital T.
Okay, got it. Yeah, I was first having problems with the acceleration, and then I realized you had to find the velocity and the height for the first height one and
Right.
velocity one. And that was confusing me because it was two unknowns. So I wasn't sure what to do there.
Well, if
But
you have two unknowns, you need two equations.
uh-huh. Two unknowns. Okay.
So you can do this in more than one way. I think the crux of the matter is right there. These two are easy. You can just write these down by inspection, and then you say, what? What do I do with that? I don't know. Well, what you do with it is use this equation here. So you have actually eliminated time from the equations, but everything here is known in terms of capital T. So just plug it in. Okay, that was good. That's a good problem.
One more question quickly.
Sure.
Sorry. Uh, could you also plug in the h and the v into another kinematic equation? Like for example, um, y is equal to y. I mean, yeah, y initial plus v initial t plus 1/2 at squared. Could I plug it into that as well, or would it not work in that equation?
Well, but the thing that you want to know is the time capital T. So the time capital T going from the ground to H1.
Uh,
So anything you write down, it better have capital T in it somehow. But capital T has nothing to do with the time after the rocket reaches H1. Right? I mean, there's no direct. How would you, if you want to write down an equation involving time for this part of the motion, that T has nothing to do with this T.
okay, right. Yeah, I think I know where you're going with this. I just need a little more time to look through it myself, but
Okay.
yeah, thank you.
Oh, all right. So some other questions? Okay. Did we discuss last time the problem of the drop of the rock being dropped into the well? I don't remember which one it is.
Professor, I have one more quick question,
Sure.
if possible. So I also had a question about 2.89, part B.
Okay. Well, yeah, we did discuss this last time, but I seem to recall I didn't give you a very satisfying explanation of this.
Mm-hmm.
So
Yeah,
go ahead. Do you just want to go over it in general, or did you have a specific question?
yeah, in general.
Okay, let's go over it in general. Okay. We have a cliff of height h. Let's let this be y equals 0 and this be y equals h. And we are doing two things. We're throwing a ball straight up with v0, and we're dropping from rest a ball from the height h. But there's a time delay between these two. So we want to arrange things such that they both hit the ground at the same time. So let's see. Let's write down y1. This is ball 1 and this is ball 2. So y1 equals the starting point, which is h, plus V0t minus 1/2 gt squared. And y2 is equal to h minus 1/2 g, but it's t minus capital T squared, where capital T is the time delay. So little t is the time from throwing ball 1 up to when ball 1 hits the ground. Or at least that's what we're going to interpret it, because we're going to set y1 equal to 0. T minus capital T is the amount of time that ball 2 is in the air after it's been dropped. So we're going to set both of these equal to 0 because they both balls are supposed to hit the ground at the same time. So the time little t that ball 1 hits the ground is the time little t minus the delay when the second ball hits the ground. But first, let's go ahead and expand this. So this is h minus 1/2 gt squared minus 1/2 g capital T squared plus 1/2 g little t times big T. Only that's not right, because when we expand this out, we get minus 2 times little t big T, so 1/2 goes away. Okay, now both of them, if we let time little t represent when the ball hits the ground, both of these are 0, and they're equal to each other. So let's set them equal to each other. They're both equal to 0 if the time represents the time hitting the ground. So we get the equation h plus v0t minus 1/2 gt squared equals h minus 1/2 gt squared minus 1/2 g capital T squared plus g t capital T. And we have some things that we can eliminate. H is eliminated. Let's see, this term is eliminated here. And we end up with V0t equals minus 1/2 g capital T squared plus g little t capital T. So let's rewrite this as little t times V0 minus g capital T. So that the time can be written this way: minus g capital T squared divided by V0 minus g capital T, and I always forget the 2. So let's remember the 2. Okay, now we have 2 unknowns here. We had 2 equations initially with 2 unknowns. These 2 equations right here with 0 put in, okay? These 2 equations with 2 unknowns. I combined them for convenience in order to get rid of the minus 1/2 gt squared. But I've still got 2 equations in 2 unknowns, which is this equation and that equation. So plugging in, I end up with, let's use another color because I'm on another thought here. 0 equals h plus V0 times t which means I'm going to have a minus sign right here. So minus V0 times G capital T squared divided by 2 V naught minus GT. And now we get minus 1/2 G, and we have to square this. So we get G squared T to the 4th divided by 4 V0 minus G capital T quantity squared. Okay, now what can you do with this? Well, if you multiply through by V0 minus GT squared, it cancels out in this term. It partially cancels this term, and it multiplies into this term. So let's write that out. We get 0 equals H times V0 minus G capital T quantity squared minus V0 G capital T squared divided by 2 times V0 minus GT, okay, minus 1/8 G cubed T to the 4th. All right, so there's a couple of different ways you can deal with this. One thing you can do is you can expand this binomial and distribute all the way through and collect all the terms and clean it up. And at that point, you'll have a quadratic equation for V0, and you can solve for V0. Another thing you can do is you can make a substitution. Okay, I'm trying to move this thing. Okay, another thing you can do is you can make a substitution, and you can let's use U as our substitution variable. Let U equal V0 minus GT. Now, if that's the case, then you have a quadratic equation for U, solve it for U, and then V0 is simply the U minus GT. And you'll get an equation for U, solve it with a quadratic equation, subtract GT from it, and that gives you V naught. That'll give you the correct answer. So it's not as elegant as the answer in the solutions manual, but I think it's more straightforward. Now, parts B and C are a little different. In parts B and C, let's get rid of this and assume you've done that. For parts B and C, you're asked something about H. Well, you need to solve this thing down here for H. And if you solve it for H, you'll get this. You'll get H is equal to some function, let's call it f of V0, divided by some function g of V0. In fact, the g of V0 is just going to be this, isn't it, if you solve for H? So part B asks you, show that if V is greater than, V0 is greater than a certain value, that there's no solution for H. Well, there's no solution for H when this function g of V0 equals 0, which means what? That when V0 is equal to G times the time delay, there's no solution for H. No height will work. As V becomes greater and greater, the height becomes greater and greater because you've got to give the first ball time to catch up to the second. So the height gets greater and greater as as V0 gets greater, the height gets greater and greater to give ball one a chance to catch up. And when V0 is equal to G times T, it's impossible to catch up. H goes to infinity. Okay, I think part C asks to find a velocity below which there is no solution for H. And that's given by whatever this numerator is. So this F of V0 equals 0. So at that value of V0, H goes to 0. And any value less, H becomes negative. So that means that we treated this H, this is Y equals 0. We treated this H as a positive number. It means that the bottom of the cliff has to actually be above the top of the cliff, if you want to think of it that way. So it's no longer possible to fulfill this condition when V0 is a number less than the value that gives F equals 0. Okay? So yeah. Okay. So you can work it out and you can come up with the numbers. Does that help?
Yes. Well, I had actually done A, but my question was on B, and specifically, it says consider the same situation. Um, well, it said that the initial velocity is 8.80. So does that mean that I would keep the same, like the 1.14 seconds later?
Hold on. Let me read it. Maybe I got the things wrong. Oh, I'm sorry. What I was talking about were C and D. So
Mhm.
part B, what must be the height of the building for both balls to reach the ground at the same time if V0 is 6 meters per second or 9.5 meters per second? That's assuming the same time delay.
1.1. Okay.
Yeah. If that's what your mastering physics said, 1.1 seconds, that assumes the same time delay. So that's just the solution for part A with different values. I'm sorry, that's the solution for H with different values of V0 and T put in.
V0 and T put in. Okay. Then, all right.
Actually,
And
big T is the same value, different values of V0.
uh-huh. All right. And then the difference between the little t and the big T is that the big T is or can you explain that one more time? What's
Sure,
the difference?
sure. Little t is the time elapsed since this guy got thrown up in the air. Big T is the time delay between throwing this one up in the air and allowing this one to drop. So I throw a ball up in the air with speed V0,
Mhm.
and T seconds, capital T seconds later, I drop a second ball. And T is given in the book as 1 second, but in your mastering physics, it's apparently 1.1 seconds.
Yeah. So then the big T would be 1.14, right? Or 1 second in your case.
1 second in my case, and whatever it says in your mastering physics for your case.
All right. Okay. Then T is the time elapsed
little t is the time elapsed since I threw this one up. And what I'm doing is I'm setting y1 and y2 equal to 0, which means that this little t is the time that it takes for ball 1 to hit the ground. And little t minus big T is the time that it takes ball 2 to hit the ground.
Oh, okay, I got it. All right, thank you.
Okay. Oh, excuse me. Okay. I wanted to talk to you about the well problem, but it's okay if you have more questions. We'll do those first.
I have
So,
a question
go ahead.
about pip 2E2. I'm not sure what it's asking me to do.
Oh, okay. I'm not sure either, but when I read it, I'll tell you. So 2E2. Oh, okay. There, for some reason, students want to do a calculation and do something with numbers with this problem. But read it carefully. It gives you a physical situation and it asks you to compare the accelerations of the two bodies. So presumably you know what the accelerations of the two bodies are and you can compare them. One is twice the other. They're both the same. They're both 0, whatever, some comparison. So let's look at the situation. Here's your cliff, and you drop a rock from rest off the cliff. Now, the second situation is you fire a bullet from a gun straight down from the top of the cliff. And you're asked to compare the accelerations of the two. So you got to figure out what the acceleration is. So what's the acceleration for the rock that you dropped?
1/2, or it'd be 4.9 T squared.
No,
Negative.
the kinematic equation says y equals y0 plus v0t minus 1/2 gt squared. What's the acceleration?
It would be negative 1/2 GT squared plus.
No. The acceleration, A, is minus g.
Ah.
Right? The acceleration due to gravity is minus g. This term here is 1/2 a t squared, where a is the acceleration. That's why we put the minus g in there. So the acceleration of this is simply the acceleration due to gravity. So what is the acceleration of the bullet being fired from the gun?
Would it also be negative G?
That's exactly correct. It's also negative g. It's a common misconception of students that somehow this has a greater acceleration. The bullet reaches the ground first, for sure. For sure, the bullet reaches the ground first because you're firing it downward with some initial velocity. And here, you're just dropping it. But that has nothing to do with the acceleration. The acceleration is due to the force of gravity, and the only force acting on the bullet is gravity as soon as it leaves the barrel of the gun. When it's in the barrel of the gun, of course, there's other forces acting on it. But as soon as it leaves the barrel of the gun, the only force acting on it is gravity. So it reaches the ground quicker because it has a V0, but its acceleration is the same. The rate of change of its of its velocity is the same, even though it started out with some initial velocity. So that's why it reaches the ground quicker, because it starts off with an initial velocity. But acceleration is the same for the two. I'm saying it over and over again, but it's an important thing to understand. Are you okay with this, Adam?
Yeah, I get it. Thank you.
Okay. Everybody else okay? All right.
Yes.
Other questions? All right. I wanted to talk to you about the problem in the well. So here's this deep well. And you want to know how deep the well is. So you take a rock and you drop it. Now we're going to ignore air friction. And 3 seconds after you drop it, you hear a splash. So the naive solution to this is to write y, and the depth of the well. So y equals 0, y equals minus h, the depth of the well. Y equals y0 plus v0t minus 1/2 gt squared. So v0 is 0 because you drop it from rest. Y is minus h. Y0 is 0. And you can write that h is simply 1/2 gt squared, where t is the 3 seconds, because you hear the splash after 3 seconds. So you know it's hit the bottom. But that's not really correct. What did we leave out? Michelle, do you know what we left out?
1 second, I'm looking through.
No, I didn't mean we left out something out of the problem that's in the text. I meant we left something out of our physical reasoning. There's an effect that we haven't considered.
Would it be gravity?
No, gravity's in there. That's where the G is. Let me ask you a leading question.
Okay.
Do you hear the splash instantaneously?
Oh, so like the echo?
Well, the speed of sound.
Okay, the speed of sound.
Yes. So it hits the bottom of the well and makes a splash, but then it takes time for the sound to travel up the well for you to hear it. So to do this problem properly, we have to include the speed of sound. So how do we do that? Well, let's redefine some variables here. Let's let T1 be the time it takes to fall. We don't know what that time is. We know it's less than 3 seconds, but we don't know what time it is. And let's let T2 be the time it takes from the splash to the sound to reach our ears. So T2 is equal to the depth divided by the speed of sound, which I'm going to call c. Now, c is usually used for the speed of light, but acousticians use it for the speed of sound. So we'll use it for the speed of sound as well. So this makes sense, doesn't it? If the speed of sound travels with c meters per second, then we multiply that by the time, and that tells us the depth of the well. Okay, but we don't know T1 or T2 individually, do we? All we know is that T1 plus T2 equals, I'm going to call it capital T. In the book, it's 3 seconds. It'll be probably some number in mastering physics because they all get scrambled. But whatever it is, we'll call it T and we'll solve the problem symbolically first. Okay, so what is T1? Well, we got to solve for this. So this is going to be the square root of 2h over g plus h over c equals t. All right, let's rewrite this first term just a little bit differently because I want to show you a trick. So I've got the square root of 2 divided by g times the square root of h. Now, I could square both sides of this equation and end up with a quadratic equation for h. So let's do it. I'll get this whole term squared equals t squared. So what's this term squared? It's 2 over g times h plus h squared over c squared. Oh, wait a sec. That's not going to help, is it? Oh, I don't want to do it that way. I'm sorry. I don't want to do it that way. Because I'm going to still end up with a radical. Ah. Okay. So the way to do that is to rewrite this as 2 over g square root of h equals t minus h over c. Now I square both sides and I get 2h over g equals t squared plus h squared on c squared minus 2th over c. All right, that's a quadratic equation in h. Rearrange it and solve for h. You're good. Here's another way to do it. Take this equation right here and make a substitution. Let u equal the square root of h. Then, of course, h equals u squared. But this equation becomes the square root of 2 on g times u plus u squared over c equals t. Now, that's a quadratic equation in u. And you can solve that for u. And once you know u, you just square it. Okay. Is everybody okay on this one? So this is a PIP problem. So you're going to write it out longhand. What I want to see, I think it's a PIP problem, is it? Or is it a master
Yes,
physics?
it's PIP.
Okay. It's a PIP problem, so I'd like to see you include the speed of sound. Oh, and you need to know the number for it, don't you? Well, the speed of sound you should take to be 344 meters per second. In Physics 223, you'll learn how to calculate that as a function of temperature. But for right now, near the Earth's surface, we're going to, at standard temperature and pressure, we're going to take that to be 344 meters per second. You can put any number you want in there. I mean, I don't really care, but I recommend that number since it's correct. Okay. Any other questions, issues, concerns, anything? You've got your chapter 2, both PIP and Mastering Physics are due tonight, right? So you must have more questions. Okay. All right, I gave you a problem to think about, or did I? I gave you the angled cliff face problem to think about, right? You guys are a little bit out of phase with the other 221 class I teach, and so I don't remember which one I gave this problem to, but the problem is this. I launch a projectile horizontally off the cliff with a speed v0. Where does it land? So, Trook, did I give you this problem last time?
Yes, Professor.
Okay, that's what I thought. Okay, you guys were supposed to work on it. So who wants to present me with their solution? Okay, let me make my expectation here clear. When I give you a problem like this and ask you to think about it and work it out for class next period, then what I want you to do is write it down on a piece of paper and solve it in detail. And then when you present your solution, you don't have to write on the board. You can just scan that piece of paper and share that document with us. So did anybody do that? Nobody did that. Okay. Well, I gave you a clue, and the clue was that the easiest thing to do is to rotate your coordinate axes so that X is aligned with the cliff face. And Y axis is perpendicular to it. So this becomes the x-axis, and this becomes the positive y-axis. And you've got the same exact problem as you have for projectile motion in 2 dimensions on a flat horizontal plane, except that you now have components of acceleration in both directions. So G acts downward like this. So the acceleration in the x direction is given by, well, let's see. This angle right here is theta, which is the angle of the cliff. So I've defined the angle theta. This angle is 90 minus theta, which means that this angle back here must be theta. Okay, so A sub x is going to be g times the cosine of 90 minus theta, which is g times the sine of theta. Now, the acceleration in the y direction is equal to minus g cosine theta. Now, the minus sign had to be put in ad hoc because g points in that direction along the y-axis. But its magnitude is g times the cosine of theta. Okay, so now you can write down kinematic equations. You can write down v sub x is equal to v0, what? Cosine theta minus G, sorry, plus G sine theta t. Let's make sure that makes sense. So V is going to be the initial velocity in the x direction. That's clearly V0 cosine theta. And it is going to have another term plus the acceleration times the time. So that's right. Let's write down V in the y direction. V0 sine theta minus G cosine theta times t. Okay, now let's write down the equations for the x and y components of the motion. So x is equal to x0, which is 0 because it's right here at the origin, plus V0 cosine theta times t plus 1/2 G sine theta t squared, and y is equal to V0 sine theta t minus 1/2 G cosine theta t squared. Okay. All right, now we want the solution. The first thing we're going to do is look at the solution to this equation. And we're going to ask, at what times does y equal 0? So our equation is minus 1/2 G cosine theta t plus V0 sine theta times t equals 0. And all I did was pull the factor of t out of this term and set y equal to 0. So what are the solutions here? Andreas, give me one of the solutions for t for this equation right here. Give me the easy one.
0.
Yes. So this factor times this factor equals 0. That means one of these two factors must be 0. So t equals 0 is a solution. Okay, Alvaro, what is the other value of t?
Is it what's inside of the parentheses?
Set what's inside the parentheses equal to 0 and solve for t. And you'll get 2 V0 sine theta divided by G cosine theta. But what can we write for added convenience? How can we write the sine theta divided by the cosine of theta? What is that, Alvaro?
Tangent?
Tangent of theta. Okay. Now, the x value at this point is simply this equation evaluated at this time. So we can write that out. X equals V0 cosine theta times 2V0 tangent theta divided by G plus G sine theta over 2 times T squared, which is 4 V naught squared tangent squared theta over G squared. Okay, and that can be simplified. Yeah, that can be simplified. Note that the units are the same, that I cross out this G with this G squared, and I get V0 squared over G for my units. So V0 squared over G are my units. Now let's check. What are the units of V0 squared? Meters squared per second squared. Divided by G, what are the units of G? Meters per second squared. Oh, great. I end up with meters for X, which I darn well better. Okay, so you know how to do this kind of problem. This actually was a simple one. Let's do a more complicated one. Let's fire a projectile up the slope. So I am going to launch a projectile with some V0 and I'm going to define the angle of this slope as theta, and I'm going to define the angle with respect to the slope that I fire V0 as phi. Now, what do you think we're going to do? Aman, what trick do you think we're going to play? Thinking back to the previous problem. Okay. Did you understand this problem? Okay, well, let's just go over it again in principle. Naively, I might decide to solve this problem by making these my axes and trying to figure out where I hit this slope. But that's kind of the hard way to do it. So for simplicity, I play a trick. I merely rotate my axes so that the positive x-axis goes down the slope and the y-axis is perpendicular to it. Then my procedure for analyzing the motion is identically the same to what we did before, except that I have two components of acceleration, both x and y, not just y. All right, so let's go to this problem and let's play the same trick. I would rotate my axis so that the x-axis goes up the slope and my y-axis is perpendicular to it. So this becomes the x-axis, and this becomes the y-axis. Now I still have the acceleration due to gravity acting that way. So let's look at some of these angles. This angle is theta. Aman, I'll let you answer. What is this angle right here? If that angle is theta, what's that angle? Look at the red. The red is a 90-degree angle. Very good. Then, Lewis, what's this angle right here between the g vector and the negative y-axis? What's that angle right there?
Theta.
That angle must be theta. Okay, I'm going to write it up here. There's not much room. All right, now we can write down the x and the y components of the acceleration due to gravity. Because my x-axis is no longer horizontal, there's going to be a component of gravity in that direction. So Daniel, what's the x component of the acceleration due to gravity? Okay, Daniel's mic might not be working. Oh, we have two Louis here, don't we? All right, well, Shifa, what's the x component of the acceleration due to gravity?
I'm not sure.
Well, that angle is theta, so that this angle here is 90 minus theta. So isn't this the cosine of 90 minus theta times g in the negative direction? And can I write the cosine of 90 minus theta in some simpler form? Shifa, can I write that in some simpler form?
I'm still not sure.
I'm sorry, Shifa, I couldn't hear you. There was a lot of noise in your background.
I'm just not sure.
Okay, well, it's the sine of theta. Okay, because they're complementary angles. 90 minus theta and theta. So a sub x is minus g sine theta. And a sub y, Benjamin, what's a sub y?
Would it be negative g cosine of theta?
That sounds right to me. So the component of g in the y-axis goes this way, so it's minus g cosine theta. Okay, great. Now we can write down all the same equations as before. We can write down y as a function of time equals y0, but that's 0 because I'm starting at the origin, plus v0y. And what is v0 in the y direction? Oh, that's a little tricky. So that would be v0 times the sine of phi, right? Because this angle is phi, this angle is 90 minus phi. Okay, minus, oh, that's times time, sorry, times the time, minus 1/2 g cosine theta t squared. And I can write down my equation for x as v0 cosine phi t minus 1/2 g sine theta t squared. All right. So I want to know what is the x value when this thing hits right there. Well, Matthew, what's the y value at this point right here?
I'm not quite sure.
Sure, right here, right on the x-axis, what's the value of y?
Oh, it's 0.
Has to be 0. So the point I want is given by the time, which is a solution of the equation, 0 equals v0 sine phi t minus 1/2 g cosine theta t squared. So I solved this the same way I did before. Minus 1/2 g cosine theta t plus v0 sine phi, factored out the t, and my solutions are t equals 0 and the solution of this. So Joshua, what's the other solution for this equation? Okay. Take a moment and look at it, Joshua. Okay, you're having trouble, Josh? Is your microphone working? Okay, that's all right, Josh. Sophia, what's the other solution besides 0 to this equation right here, that equation? All right, Tuan, what's the solution? All right. Okay, the solution is the solution of minus 1/2 g cosine theta t plus v0 sine phi equals 0. Because either t is 0 or this thing is 0 to make 0. So solving for t, we get 2 v0 sine phi divided by g cosine theta. Phi and theta, of course, are not the same angles, so that doesn't become a tangent like it did before. All right, now the task to find the range is to simply plug this time into the equation for x. And if I plug this time in the equation of x, then x becomes this range. This distance from here to here. So let's take a break. And I will see you back at 3 o'clock. In fact, let's make it 3:15. And I want somebody to plug this in, work out the algebra, and give me the final answer to the range. You do it on a piece of paper and scan it and share the paper with us. Or you write on the board. Either way. Okay.
I have a question. So in the y and x formulas, t is squared is like at the end. Is that just like given in the formula, or is it because of the specific problem?
No, these are the kinematic equations. For the velocity of acceleration, there are other form of x equals f0 plus v0 t plus 1/2 acceleration t squared. That came from integrating v equals dx dt.
Okay.
Wait, but the t squared is the integral. Okay. All right. 3:15. Okay. Who would like to finish this problem?
Can I give a go?
Yes, you can. Are you going to share with us a PDF, or do you want to write on the screen, or what do you want to do?
Maybe just around the screen is good.
Okay, do you want me to put up a new screen for you, or do you have room here?
I think I would try to make it happen here.
Okay, good.
Uh,
Okay. There you go. Okay. Very good. So that X stands for the range when Y equals 0. So you could call it X, you could call it R. And you've got V0 squared. Very good. Oh, okay. You return control of the screen? Thank you. This sine 2 phi, this symbol is a phi, by the way, for those of you who may not recognize it. The sine 2 phi is 2 sine phi cosine phi. So you combine those and combined everything so that you can put it under the same denominator. That's very good. Good job, Trook. Hold on a second. I'm going to give you an extra credit point.
thank you, Professor.
Okay, thank you. Okay. I'll give you an extra credit point. And every extra credit point you get for anyone in the class, I'm going to add 1 percentage point to your final grade. So you need to get an 86% to get an A. So if you have 85, but you got an extra credit point, you've gone from a B to an A. So good job. Now, let me write this again. We have the range equals V0 squared sine 2 phi minus 2 tangent theta sine squared phi, and that whole thing is over g cosine theta. Okay, great. You know what? I want to write this differently because I'm going to write this term differently here. So I'm going to expand that back out as 2 cosine phi sine phi. And there's a reason for that. I want to differentiate, and it's going to be easier to differentiate. Okay, so this is the expression for the range up the slope. It's called the slant range because it's not the horizontal range. It's up the slope. It's the slant range. Now, what is the maximum possible slant range? Well, how do we maximize a function? Sophia, how do we maximize a function?
Hello, sorry.
How do you maximize a function? What do you do?
I'm not sure.
Well, let's look at this for a moment. Let's say you have a function f of x, and you have, let's say it looks like this. And you would like to know what is the value of x at which that function is a maximum, a local maximum. Well, right here at the maximum, what is the value of the derivative?
X prime? Are you asking the derivative?
Right there.
Oh,
Right
okay.
there.
Yeah.
The slope
It's
is
zero.
that. It's 0. Very good. Okay. So first thing you learn in optimization theory is a function of a single variable. If you want to find the local extrema, which could either be maximum or a maximum or a minimum, you take the derivative of the function and set it equal to 0. Now, in this case, we have a function r, which is a function of phi, the launch angle. We'd like to know what launch angle gives me the maximum range. So what I do is I take dr d phi and set it equal to 0. Now I'm differentiating with respect to the phi, not with respect to theta. So the g cosine theta is just a constant, and it's common to both terms. The 1 over g sine theta is common to both terms, so we don't even need to carry it around. So let's just oh, I forgot something here, didn't I? There's a v naught squared here, isn't there?
Yes, I was going to ask you if one was supposed to go
Yeah, I
there.
just forgot about it because I was thinking of putting okay. So the 2 v naught squared and the g cosine theta, those are just constants that are common to both terms. So let's differentiate with respect to phi this function. Cosine phi sine phi minus tangent of theta, and theta again is a constant, sine squared phi. So who would like to do that differentiation for me? You can use product rule for this and chain rule for that. Who wants to do it?
I could do it.
Okay. So you can just tell me what the terms are, or would you rather write?
I'll just tell you.
Okay.
So for the
So for this first term,
it would be negative sine squared phi plus cosine squared phi
okay.
then it would be minus oh wait, tan theta. Okay, never mind. It would be 2 tan theta sine phi cosine phi.
Okay. Now we want to set that equal to 0 and solve for phi. Okay. So let's clean this up and we want to solve this for phi. You know what? Let's write this a different way after all. Let's let this be, oh. No, wait a minute. I made a mistake, didn't I? This isn't right. It's 2 v naught squared cosine phi sine phi minus 2 v naught squared. No, this is correct. Okay. So let's write this as sine 2 phi minus 2 tan theta sine squared phi. Okay, now Aurelio, go ahead and do it again for me.
It would be wait, 2 cosine 2 phi
Okay,
minus 2 tan theta times 2
right.
Sine phi cosine phi.
Okay. And we can cancel out, oh, set this equal to 0. And we can cancel out the 2's. So get rid of this one. Okay, now let's solve this for phi. And what do we end up with? We end up with cosine 2 phi is equal to 2 times the tangent of theta sine phi cosine phi. Oh, all right. But 2 times sine phi cosine phi is just the sine 2 phi. So cosine 2 phi is equal to tangent theta times sine 2 phi. All right. And now we'll go up here to the right. We're going to get the tangent of 2 phi is equal to 1 over the tangent of theta. I'm just going to write that as the cotangent of theta. So phi is equal to 1/2 the arc tangent of the cotangent of theta, right? Okay. So that's our answer, at least in one form, although we can simplify it. So for this problem of shooting a projectile up the slope, we have the range given by this equation, and the maximum range occurs when phi equals this value. But we can write this in another way. It turns out the inverse tangent of the cotangent of theta is pi over 2 minus theta. So the optimum angle becomes pi over 4 minus theta over 2. So let's go back and look at our picture again. Okay, so the optimum angle theta here, so theta max equals pi on 4 minus theta on 2. Let's look at a special case. Let's look at the case where theta is equal to 0. If theta is equal to 0, then I'm just launching on the horizontal plane. And what value of phi gives me the maximum range if I'm firing on a horizontal plane?
45.
45 degrees. And what's pi on 4?
45.
45 degrees. Okay. So it makes sense, our solution. Now, in order to determine what the maximum range actually is, we have to take this value of phi and actually substitute it here. No big deal. Just substitute in 45 degrees minus theta on 2, whatever theta is, and you can determine what the maximum range is. So let's say that the angle here is 45 degrees. Then the optimal, so that's pi on 4. So pi on 4 minus pi is pi on 8. So the optimum angle here is going to be 22.5 degrees. And you can plug in 22.5 degrees here, and theta is 45 degrees, and see what the maximum range would be for a given V naught. Okay. Does anyone have any questions on this particular problem?
Would would it matter to you how we wrote for the equation where you have R?
Yeah,
Truck, she did the
she wrote it as X.
yeah, and
That's
she
fine.
she did it as the sine of 2 phi, where
Yes.
I have from here, I just factored out 2 v naught squared and a sine phi.
That's
Would
fine.
it matter? Would it matter how we wrote it?
No,
Okay.
no. If it's all the same, it doesn't matter. Provided it's right, it doesn't matter unless there's a special reason that I ask for it in a certain form. But I can't think of why I would do that. All right. Any other questions on this? That was a problem that looked really formidable to begin with, but as you worked your way through it, it's not so bad, was it? Okay. Nobody has any questions on anything? All right, then let's continue lecture. So the second to last subject in chapter 3 is uniform circular motion. And by uniform circular motion, what I mean is motion in a circle with constant speed. So Adam, is the velocity constant in this motion?
Yes.
Okay, I said constant speed, right? So what's the difference between speed and velocity?
Oh, velocity has a direction.
Right,
Magnitude.
right. It's speed is the magnitude of velocity. And in uniform circular motion, my velocity is constantly changing. However, my speed is always the same. So let's analyze this situation. Let's consider a point right there. This is the radius of the circle. And at this point right here, I have a velocity vector that's tangent to the path and looks